Welcome, everyone. For today's prep, we're going to look at a few examples for how to differentiate the natural exponential function. And we've looked a little bit at this. So first, let's just remember what the natural exponential function is. So we know all of our exponential functions go through this point 0, 1. And the way we define e to the x, or this constant e, it's the one special exponential function that has a slope equal to 1 at that point 0, 1, where all of our exponential functions go through. So all the exponential functions go through this one specific point. So we pick the number e, or we define the number e, which sits in between 2 and 3, and e to the x has slope equal to 1. And it's this property that kind of makes its derivative nice. So we looked at the formula for the derivative of e to the x. Derivative of e to the x, really nice. It's just e to the x. So let's try some examples now where we actually use this. So let's look at example 2. Want to find the tangent line to the graph of e to the x when x is equal to 1. So let's remember, this is kind of review. How do we find the equation of a tangent line? Well, there's three things we need. We need the x-coordinate for our point, we need the y-coordinate for our point, and then we need the slope of our point. And in this case, the x-coordinate we're given. So the x-coordinate here is just 1. And then we get the y-coordinate by using our original function and plugging the x-coordinate into that. And then we get the slope of our tangent line by using the first derivative, and we plug the x-coordinate into our first derivative. All right, so we're going to need f prime, so let's calculate that. So this is where we're going to use our new idea here. So the original function is f of x, which in this case is just e to the x. And if we differentiate that, it's not going to look like we do anything, but the derivative of e to the x, really special, it's its own derivative. So f prime is also going to be e to the x. All right, so let's find the y-coordinate for our point. So we're going to plug 1 in. X equals 1 into our original function. So we're going back to the original function here. And when we plug 1 in for x, we're going to get e raised to the power 1. And we don't normally write terms with an exponent of 1, so we could just leave this as e. So don't forget, e is a perfectly good number. It's kind of like pi. So pi is approximately 3.14. E is approximately 2.71. So it's just a fancy name for a special number. All right, so then to get the slope of our tangent line, we're going to plug 1, our x-coordinate, into the derivative. So we're going to plug x equals 1 over into our derivative here. And we end up with the same thing because, well, those two functions are the same actually for this one. So we have our slope of our tangent line is e. So once we have these three ingredients, then the next step is we plug these into our point slope formula. And this is going to give us the equation of our line. So what's the point slope formula? Well, it's y minus the y-coordinate is equal to m times x minus the x-coordinate. And we just plug in the pieces. So we know our x-coordinate is 1, so that'll go there. Our y-coordinate is e, and then our slope is m, is also e. So if we plug in the pieces, we get y minus e is equal to e times x minus 1. And that is our tangent line. And we could solve that for y, but perfectly fine to just leave it like that. All right. So really, this is all review. The only thing new here is just how did we get the derivative? Well, we want differentiated e to the x, and we got e to the x. Let's try another example of practicing this. So example 3, we're going to differentiate a couple functions here, and each of these is going to take our special derivative rule, some of our advanced derivative rules. So let's look at the first one. We have 1 plus x squared times e to the x. So even though it's not written, there is some multiplication here. So we've got some variable stuff here, and then we're multiplying, and then we've got some variable stuff here. So we've got x terms in two spots, and we're multiplying in between the two. So for this one, we're going to use product rule. All right, so our derivative in this case, if we're applying product rule, well, let's write down our two copies of our product. So we'll have 1 plus x squared times e to the x, and then 1 plus x squared times e to the x. We put a plus sign in the middle. And then with product rule, we apply the derivative to the first term in the first copy, and then in the second copy, we apply the derivative to the second term. Just kind of standard product rule here. So nothing new yet, but now when we go to differentiate these, especially that second one, that's where we're going to be kind of seeing our new piece of info. So if we differentiate the 1 plus x squared, we get 2x. And then we have times e to the x plus 1 plus x squared. Don't forget the parentheses here. And then when we differentiate this e to the x, well, derivative of e to the x is just e to the x. So there we go. And we're done. We have our derivative. We're done. Now in this case, it does actually simplify a little bit. So both of these have an e to the x that we could factor out. So sometimes when differentiating these exponential functions like this, we can do a little bit of factoring. Again, not absolutely necessary, but it can be helpful. So if we factor an e to the x out of here and an e to the x out of here, what are we left with? Well, we have a 2x plus 1 plus x squared. And if we rearrange the terms, just to kind of make them go in order, we have e to the x times 1 plus 2x plus x squared. All right, so again, perfectly fine if we're just differentiating just to leave it there. But if we wanted to do stuff with the derivative, you'd probably want to factor it like that. All right, so let's try another one. 1 plus e to the x over 2x. So when we look at this one, it's a fraction, it's a quotient, and we've got x terms in both spots, the top and the bottom. So when there's x's in both places, we want to use the quotient rule. All right, so how is our derivative going to work for quotient rule? Well, we write this quotient as a product. So it's the top function, 1 plus e to the x, times the bottom function. And then, just like product rule, we do two copies of that. In the first copy, apply the derivative to the first term. And then in the second copy, apply it to the second factor. And then with quotient rule, we put a minus sign in the middle. And then we make this into a big fraction, and we square the original denominator. So 2x, the whole thing squared. All right, so now we want to finish differentiating. So we've kind of differentiated our way through the fraction, but now we get to do the top and the bottom here. So if we differentiate the 1 plus e to the x, again, this is where we're going to kind of use our new piece of info. So the derivative of 1, when we differentiate that 1, that's just going to be 0. And then the derivative of the e to the x, well, e to the x when we differentiate just stays the same. So the derivative of that first term is just going to be e to the x. So this whole top derivative that we did ends up just differentiating to e to the x. And then we have our 2x minus 1 plus e to the x. And then differentiating 2x, that's kind of usual stuff. We just get 2. Okay. And normally we don't need to do too much in the denominator when we do quotient rule, but in this case, we can square this out. So because there's multiplication, it's 2 times x, we can distribute the squared to both the 2 and the x. So we end up with 4x squared. And we could simplify this down, Maybe there's a little bit of multiply this out, distribute the negative, but that's pretty good. All right, so we'll practice a few more of these in class, and we're going to start to look at what happens if we kind of make these exponential functions a little bit more complicated. How does the derivative work in those cases? So we'll see you then. Bye-bye.